Alright, I'm going to discuss with you some practice tests here kind of quickly just to explain what I've done in all of these. So we have two charges already existing here. One, we don't know the charge, Q2, and one, we do know the charge is Q1. A positive charge of 1.1 microcoulombs is placed at 1 centimeters and observed to have an acceleration of 0.22 meters per second squared to the right. Our job is to figure the magnitude of charge Q2. Okay, well, let's take a look at this here. Well, we now know if I place a charge at position 1, which is right here, it is going to definitely be repelled by this charge here. And this one's located at 1, 2, so that would be 3 away from it. And then Q2, of course, would also be interacting with it, and it looks like it's 2 away. So we're going to apply the superposition principle. Okay, first though, we need to find the electric force's value. Well, we're just going to set that equal to mass times acceleration. Remember to convert mass to kilograms. So that's this value here, 0.00011 newtons. So I'm going to set that equal to here. Okay, now I know I have a force vector, okay, that is going to be pushing that one across to the other side. We know that Q2 does have a positive charge, so it's going to be pushing back in the other direction on that positive charge. So we're going to take the difference between those forces and set that equal to MA. So here's our MA. We're using KQ over R squared for both. This is from the 3.3 microcoulomb charge. This is from the unknown charge, and we solve for Q2, and it's 1.5 microcoulombs. Let's continue. What is the value of the electric field? So I'm going to take 0.00011, and that's the electric force there, and I'm going to divide it by the charge, okay, that exists there. And the one that exists there is the 1.1 times 10 to the minus 6, and I'm getting 100 newtons per coulomb. The direction is to the right. I know that because the positive charge is accelerating to the right. All right, next, if a proton is moved from infinity to a position of 5, how much work is done on the charge due to the change in electric potential for this proton? Okay, well, why don't we calculate the electric potential that happens? Okay, so we're putting that proton at position 5. So this is 0, 1, 2, 3, 4, 5. So that's position right there. Now there are 3 charges that will add up to be the potential at that position. We have the one that we placed at position 1, then we have Q2 and Q1. So we're going to use the equation volts equals KQ over R, and we're going to add all those up. So volts equals KQ over R plus KQ over R plus KQ over R. And it looks to me like we're getting a 1.3 times 10 to the minus 6. Okay, they are all positive charges, so they're all going to add up. Remember, this is not a vector. Okay, I'm going to multiply that 1.3 times 10 to the 6 volts, and I'm going to multiply that by the charge of a proton. Okay, so we have 0 potential at infinity. We bring a charge up under the presence of these 3 charges, and we calculate the potential using KQ over R and just add all of them together. Okay, what is the change in electric potential for this proton? Okay, now move the proton from 5 to minus 3. Okay, so we're just going to redo the same calculation again, now with different radius values. And then we're going to have a value of 3.5, okay, times 10 to the 6th, okay? And then how much work is done. So we're going to subtract our answer to the electric voltage from the first calculation from the second. We get 2.2 times 10 to the 6 volts. And one more time, multiply that by the charge of a proton to get the change in potential energy. So there's that question. All right, next question here. 3 charges are located at the corners of a 10 centimeter equilateral triangle. Determine the resultant electric potential at this position. Okay? All right. For the first case, all we're going to do is KQ over R each one of those. Okay, of course, I need to determine the distance. I know from here to there is 10, here to there is 10, from here to there is 5, here is 5. Then I have to use Pythagorean theorem to find out there's 8.7 distance here. Now this is the position that we're trying to find. This is position X. So This is a negative charge, and it looks like the other two are positive. So I'm going to volts equals KQ over R for each of these. This one will be negative because that's a negative charge. I'm just going to add all those together. So we have a distance of 0.05 centimeters, 0.05 meters, and 0.08 centimeters. So here you just see me adding up all the volts equals KQ over R. Alright, now what's the difference between that and finding electric field at that position? Well, electric field is a vector. So now we need to determine the directions of this. Okay, so if I put a positive test charge here, this -4 charge will attract it that way. Therefore, E1 is going left. This 6 would repel it away. E2 is going, okay, to the left. This charge here is positive and will be pushing down this way. Therefore, that's why I've got electric field 3 pushing this way. So these are 2 X's and these are 2 Y's. Okay, so you're seeing me doing KQ over R squared for all of those. Okay, I'm going to summarize my X's. I'm going to summarize my Y, which is only 1. When I get done with that, I'm going to Pythagorize and inverse tangentize, okay, to get my answer. Remembering this is a vector. Okay, and my final resultant vector looks to be 5.8, okay, times 10 to the minus 12 newtons at 5.7 degrees south to west. Okay, so how do I get from there to get newtons? Well, if my electric field is 3.6 times 10 to the 7th newtons per coulomb, all I do then is take my charge of my proton and multiply it by that electric field's value, and I get electric force. Remembering that force electric is electric field times charge. The next page is the next chapter, so you do not need to worry about this one at all. Okay, and we'll produce my next video, okay, dealing with the AP questions, and we'll discuss more after that.